SwayamPrabha. Digital India. Educated India.
Ready with the MATLAB, very powerful method of taking care of non-linearities in an estimation problem. Okay, so the original problem of ill-posedness, that means small changes in the signals could cause large changes, okay, in the output. So this is characteristic of any nonlinear problem. So I told you the three conditions have to be satisfied for an inverse problem, right? Existence of a solution must exist, solution must be stable, solution must be sensitive, not sensitive to errors, and so on. So because one of these conditions is always usually violated, one or more of these conditions is violated, it was a dreaded field. Which was a dreaded field? Inverse problems. Forget about inverse problems in heat transfer. That is a very new field. Inverse problems in science and engineering, though there are a lot of inverse problems, right? You want to take a telescope, look at the data from some other planet, and you want to figure out what is the molecular composition of the atmosphere there and all that, right? So you want to look at the absorption spectrum, you want to look at the emission spectrum, you want to do cosmology, you want to do astronomy, you want to do geology, whatever be the field, okay? Or you want to do fluid mechanics. So heat transfer, of course, all right? So because of the funda that one or more of these conditions is usually violated, people did not go anywhere near that, okay? Then we told you that the American professor Beck started looking at the inverse problem, the re-entry missile, because they were looking at the space program was developing in the US. They wanted to get an idea of the heat flux, but they were not able to measure the heat flux because any flux gauge will blow up. So they had to put a flux gauge somewhere deep inside, and they have to solve an inverse conduction problem. So originally inverse started as inverse heat conduction problem. Okay, that's how it started. So a lot of mathematicians entered the field. Okay, and mathematicians working as heat transfer professors. Professor Ozisik was a very famous professor. Okay, Professor Nekati Ozisik is Turkish. So he died, of course, now. So he has written a lot of books on inverse, and his student is Professor Orland. Professor Orland will be a little senior to me. He must be in the mid-50s. Okay, he's a good friend of ours. So he's a Brazilian professor. He works in the Federal University of Rio de Janeiro. He is a PhD student and he's continuing a lot of inverse work now. Okay, so but they're all mostly very mathematical. They don't do many experiments. They work on algorithms, testing, regularization, and so on. Okay, the idea of regularization came from the Russians. Okay. So Professor Tikhonov, 1906 to 1993, is a famous Russian mathematician. He first figured out how to handle these nonlinearities, how to handle the ill-posedness. Okay, so basically, if you consider, consider y equal to f of x I a1 to a m. Okay, so a1 to am are the parameters. Okay, this is general representation. This is a single variable problem. Of course, you can have x1 of I, x2 of I, x3 of I, and so on. Okay, a1 to am are the parameters. So normally we do the s equal to sigma I equal to 1 to n. Okay, so yi minus f of xi a1 am whole square. So we try to minimize s, right? Normally, because the forward model is never perfect and all the measurements are subjected to error. So please note that s can never be made zero. It's impossible. If somebody tries to make it zero, that means they're trying to fool us, because there'll be natural error in any measuring process. Okay, and there is any solution procedure. Okay, unless you're taking a very simple problem. Okay, so therefore errors will be there. We always try to minimize the S. We saw the least square regression, and then if it's a nonlinear form, how to start with an initial value of a b and proceed forward and so on. So the idea of minimizing the S, okay, this was the boon and this was the bane. So Tikhonov figured out that if you keep on minimizing the S, there could be situations where the initial guess can be far off and the nonlinear problem can go for a 6. Therefore, he said that something must be added to S. Okay, something must be added to S, and which can be a damp, which can be a dampener, right? We say, it rain dampens the spirits of the cricket match at whatever. Wankhede Cricket Stadium, whatever. You must have seen news items. So you add a dampening. In fact, this was precisely what was done by Leeuwenberg and Marquardt, right? Okay, this is what was done by Leeuwenberg and Marquardt. Lambda into I and lambda diagonal of Z transpose T Z, basically a damping. So basically, therefore, basically MA and LMA are basically damped least squares. So the Z transpose T Z, if the determinant becomes, if that becomes a singular matrix, that means the determinant becomes 0 or close to 0, it can go for a 6. So this can be calculated mathematically by what is called the condition number of a matrix. So it's basically the condition of, so it's called about, we say about ill-conditioned systems and well-conditioned system. If Z transpose TZ, Z transpose TZ mod of determinant of that approach is 0, then it becomes ill-conditioned. Therefore, to make a ill-conditioned system to reasonable conditioning or into a reasonably conditioned system, you add a dampening so that very low determinant value of Z transpose TZ is taken care of. And so the Z transpose TZ doesn't cause much mischief in our search for the truth. The search for the truth is actually A1, A2, AM. See, this Z transpose D, this all that is something which is going on in our mind. Reality is there is a time, there is a temperature, there are some parameters which cause the temperature. I want to find out this differential equation, this least square, all that is a mathematical construct. It is something which is going on in our mind, which the system does not know. That is our way of trying to understand the system. The system will behave according to its dharma. So please never be under the illusion that science will get it right. Science is the science of making a y equal to Taylor series, or why should you stop with linear? Who told you that we cannot look at higher order terms? How can you say that that is negligible? For example, I say if it is not negligible, science has helped us to solve problems, but don't think that this is the be all and end all. That is sometimes the problem with undergraduate education, even up to masters or PhD. You think that, oh, this is okay, it is great and all that, but basically it is one route. It is a route to solve the problem. The original problem is something is causing the behavior. I want to find out what is causing the behavior precisely, so that I can design some equipment or take care of it and so on. So all this jamela of defining a Z, Z transpose D, lambda, I, all that is because it is our inability. It is our inability to directly get the A1 to AM by just looking at theta and time. What is most important is for a given set of, for 6 time instance, I have 6 temperatures, but I don't know what is causing that. So all this forward model, this thing, all that is my way of understanding the real world. So mathematics and science are helping me, but this is one way of understanding the world. Now, when you get into that mathematics, that creates trouble. What creates trouble? Z transpose D, Z creates trouble because the determinant sometimes can be close to 0. Therefore, a new set of scientists are coming. They'll say, I will put a lambda of I put a lambda of diagonal of the diagonal of Z transpose D, Z, blah, 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 all that. And we are able to make progress. So we are able to solve some more problems which originally the Gauss-Newton algorithm cannot solve. Now, even with all this, suppose you are not able to solve. There are situations where the Leeuwenberg-Marquardt doesn't work. Is there a more general way of looking at the dampening the least square so that we can get a better handle of the problem? So these ideas, highly mathematical ideas, you can see that many of these have come from Russia. Okay, Russians are extremely good in mathematics. Okay, so what he proposed was we should actually minimize not this plus s plus something. Okay, he said let's do okay. So this s plus some lambda whole square. Okay. So this lambda is again a non-negative damping factor. This we already introduced because now this lambda is not giving any trouble to us because we already lambda may be a trouble for the uninitiated, but you're already initiated by the Leeuwenberg-Marquardt. So this lambda is some non-damping, non-negative damping factor, and this L is something. So that L is something of Lagrangian or something. What is that L? So there could be various proposals for the L. Once you have various proposals of L, which should be, which are likely to be either the functions of Z or it could be a function of A and B or a mixture of both, whatever. There should be something which will take care of lambda into that should take care of the S so that we should be able to get a handle, and we'll prove in some cases that this is better than just trying to do OLS. What is OLS? Ordinary least squares. This was what Tikhonov proposed, and then what he said was now for this problem, for the problem under consideration, that is y equal to theta equal to a into 1 minus e to the power minus e to the power of 1. So what this one proposal is, okay, s equal to I equal to 1 to n ri square, that is the residual, plus lambda sigma. This will come later. So let's say, okay, so sorry, so this will come later. So the proposal is the sum of the residuals plus lambda times into sum of the squares of all the parameters themselves. How did he get this idea? We don't know. I don't know what. He's not there. He died 30 years back. I don't know. Maybe his students talked to him or his co-workers talked to him. And then somebody, how did he get this idea? Why did he get this idea? Why is it working and all that? Somebody has already proved. We can have a proof of all that. And how did he get this idea that the second term must be the sum of the squares of the parameters themselves? Which means we want to minimize, yes, the second is an additive term first. So it's a dampening term. It's like a viscous damping. It's like a spring mass system. You put a viscous this thing and a damping pot and all that you have studied in your engineering mechanics. So it is always a plus term because it's sum of the squares. Therefore, for some reasons, it penalizes large values of the parameters. You see that? Okay, for some reasons, it penalizes large value of the parameters. Okay. So let us proceed further for the problem under consideration. So this S will be I equal to plus lambda into A square plus B square. Okay, this is 4. Now you can do dou S by dou A equal to 0. 2 sigma 2 sigma Ri into dou F by dou A plus 2 lambda A equal to 0. Now I'm giving you the Tikhonov, original Tikhonov proposal and the mathematical proof. Huh? Don't ask me how we got or why it works. Okay, we are just seeing the mechanics. That means what is the method? That's all. How did he get this idea? God knows. How did Planck get the idea S equal to NH2? I mean, why did he get it? We don't know. We can't answer that question because at some point, then it's not the analysis, it's not the reasoning. Intuition takes over. All these people got this E equal to MC square something. Other people, we can defend it later on. But the original guy who got it, there is some inspiration. We don't even know how it comes. That is the intuition, right? Even 30 years of formal learning, we may not get it. Okay. But some people get it. That's how it Why should it be S equal to NH mu and there's an elliptical phase space, N can vary 1, 2, 3. How did Planck ever get that? Okay. So I think that Planck is one of the highest scientists. Okay. I still don't know because I am working in radiation. So I still don't know how we got it. Okay. Anyway, so dou S by dou B. It didn't come from school. It didn't come from attending classes. It didn't come from writing papers. It basically just looked at it for such a long time. He was totally immersed. So he identified himself with the problem. So the problem and Planck became one and the same. The knower and what is to be known and the process of knowing, they all merged. And then we got something spectacular, right? Okay, so this is minus I equal to 1 to n Ri do B. Okay. Plus 2 lambda equal to 0. Okay. Now, so two equations and two unknowns. But closed form solutions may not exist. We saw that if you just put the term y equal to a into 1 minus e to the power of minus bt, you can see that the closed form solution you will not get it because the dou f by dou a and dou f by dou b both contain the parameters a and b, which are the parameters you want to retrieve. Therefore, there's a nonlinearity inbuilt because you cannot proceed further unless you assume the value of a and b. That is a nonlinearity. But closed form solutions for a, b may not exist for all problems. Okay, so we employ an iterative technique. Okay. What is the iterative technique? So we say that f of a n plus 1, f of a plus j a delta a. This is called the Jacobian. Dou f by dou a. That is called the Jacobian of a, which is the sensitivity matrix. Similarly for b. Okay, so to do that, then it lead to a lot of steps, which I'm skipping now. Suraj, at the end of the class, you please send the proof by WhatsApp and email to them, right?
Okay.
PDF. Okay, so we have the proof. We have already written, handwritten proof is available, but I'm just keeping it in the interest of time. Okay, so once you go through a series of steps, okay, which is some more mathematics, algebra, finally it results in this. So Z transpose T, Z plus lambda I. So this looks familiar to you on delta A. So this is familiar. The left side is familiar. It looks like the Markov algorithm, but the right side is little different. Minus lambda of A. Suraj, is this right?
Yes, sir.
Is that right? Now let me check it. So this is 2 cross 1, right?
Yes, sir.
So this is 2 cross 2, and this is
1 cross 2.
D.
Yes, sir.
What is D?
Forcing vectors.
1 cross 2. Is that correct?
Not 1 cross 2, sir. Not 1
Not
cross
1.
2.
Not 1 cross 2. What is Z transpose? 2 cross N.
2 cross 1. N cross 2.
Hey, Suraj, you are not helping me. Huh?
Yes, sir. 2 cross.
You're taking me to a far away from the solution. Okay, so I just want, okay, now you see, this is the Tikhonov. Please note it down. So this is how we got it. We still don't know how this guy got it. Huh? So subject after subject, prof after prof in all the universities, whoever is teaching estimation, inverse, data science, whatever, least square. If you proceed, Tikhonov. So long live Tikhonov. He will live for another 100 years. Okay, so he has done something outstanding. Okay, so this is Tikhonov regularization. Please note that if lambda equal to 0, this will go, this will go. If lambda is equal to 0, what happens to this?
GNA, sir.
So Suraj, I know that I wanted somebody else in the class. If lambda equal to 0, it reduces to GNA. Is that clear? Just do a thumbs up. Don't get drowned in the mathematics. Even as a student, I always used to check. So we have to check what is called. You know what I did now? There is a name for that. What I did now is called the asymptotic correctness check. Asymptotic correctness check is a technique which can be used in science and engineering and mathematics. You take you're working out any expression, you take it to the limits of something approaching 0, something approaching infinity, then it should reduce to a form which is familiar to you. Once it reduces to form familiar to you, that it reinforces the learning, the cognitive experience is enhanced, and this will permanently remain. And so you will get convinced that because for an asymptotic variant, the problem is giving a solution which you already know, which has already been confirmed by other investigators. There is no reason to believe that if the asymptotic correctness, if the asymptotic variant is relaxed, and then you're working out the actual problem itself, it should suddenly misbehave. Why it will behave properly in its asymptotic variant? Why theoretically it is possible? It is unlikely in nature that if it works for lambda equal to 0, suddenly it will not work for some other lambda. All right. So this is a technique which we use it for validation. So as an editor, when I reject papers, I will say that somebody will say, I cannot validate with experiments. I said, if you don't validate with experiments, just conjecture. You're just putting mathematical theorems in an engineering journal. My journal, I will say, you want to find, finally, it's not whether you know whether you can prove a theorem. We want to make a heat exchanger. We want to make some rocket go up and launch a satellite. We want to find out something. We want a car which works. We want a car even at 120 kilometers per hour. If it gets in an accident, the occupants are safe. You do your modeling, you solve your equation, whatever. Finally, there should be some reality. There should be something. Okay. Maths is only a tool to get there. Okay. Maths for the sake of maths is something else. But I am not in that category because I'm an engineer. Okay. So I think you're not students of maths. So maths for the sake of maths, only a few people a society can afford. Because usefulness of what you and I do will be a question which everybody will ask. Okay. All right. So this is the original Tikhonov regularization. Okay. And if lambda is iteratively solved, if lambda is iteratively solved, we call it as the Alifanov. He is a student. He's still there, I think. I think he's a senior professor now somewhere. He's a senior professor somewhere in Russia, Alifanov. Okay, so he's also a reviewer for our journal. Whenever I get inverse papers, I send to Alifanov also a few papers, and he's quite good at. He's quite prompt in reviewing. Okay, so if that is iteratively solved, means you start with you start with one value of lambda, then change the other value of lambda, and see how the solution proceeds, and then dynamically update the value of lambda. So apart from guessing for A and B, you also guess for lambda. That is called Alifano regularization. We are not teaching Alifano regularization is there in the syllabus. So you just put the tick mark. Go back to your first class, your syllabus. So Tikhonov, Alifano, you can see how much we have covered. Okay, up to today's class. All right. Now let us take the problem number. Just go to what is the problem number now?
12.
12. Very good. Problem number 12. Please take it down. Revisit the revisit the problem involving GNA. Problem number 12. Revisit the problem involving GNA. Okay. With the same set of initial guesses, revisit the problem concerning or involving GNA full stop. With the same initial guesses for A and B. With the same initial guesses for A and B. Perform 2 iterations. The same initial guesses for A and B. Perform 2 iterations with the Tikhonov regularization. Perform 2 iterations with the Tikhonov regularization. Okay. Take lambda equal to 0.001. Okay. Consider DNA problem. Consider DNA problem. A equal to 35. Okay. Suraj, can you show it? So let's save some time. It's 10:30. You may be startled. How can sir finish in 20 minutes? All this Z transpose T, Z, D, all that is the same, right? Okay. Only small addition is required for the Tikhonov. Suraj, I will allow you to share the presentation now. 1 second, Suraj. So yesterday's class of the Liebenberg-Marquardt also we did the same Z transpose T. So with the same initial guesses, so your Z will be the same, your D will be the same, many things will be the same. So only the right side will be different. Okay. So let us do the identity matrix, all that we did yesterday. Okay. Okay. Suraj, 0.001. Suraj?
Yes, sir. Change, sir.
0.001. Very good. Okay. Now, please look at the, please start talking now. Can you talk? Or you want me to talk? Huh?
Yes, sir.
You want to talk or I should talk?
Okay, sir. I talk, sir.
Oh, okay, you talk. Okay, fine. All right.
Sir. This is initial guess I already given 35.004. And only change is here.
Okay, just Suraj, you just wait. Go to the left side and show me the Z. Okay, so Z. So Z equal to. Tell me the values 0.0392.
0.1513. 0.2709. 0.4265. 0.5543. 0.6964.
Over.
Yes, sir. Second column. 336.28. 1217.9. 1217.9. 2015.8. 2790.1. 3151.4. 3166.7.
Okay, so we got this. So this is the Z matrix. So Z this also we can do. Okay, so Z transpose T Z and lambda. Z transpose T Z is what?
Yeah, okay, sir. Z transpose. 1.0.
Wait, Suraj.
Okay,
Z transpose T Z.
1. Yes, sir. 1.07. 18. And 5885.48.
Yeah, so this is symmetric.
Yes, sir. Symmetric, sir. And 3340.
3340.
4118.
3340 4118.
1 4.
1 4.
Yes, sir.
Now, so far so good. This is the same as the GNA plus now add this Z transpose T plus lambda I. Lambda is 0.001. So what is this? 1.07?
28
Ah,
and
5885. Same.
yes, sir, same, sir. This is also
This won't change at all. No? This fellow is 0.24. That's all.
yes,
This
sir,
won't
same,
change.
sir.
It's so big.
Yes, sir.
So this won't change. So actually, if you see the left hand side is not changing much, but the right hand side will change. Okay. So we got this Z transpose T plus lambda I operating on. So the right side is what? What is this?
3314.
Huh?
331427.
3314 or 33.14?
Yes, sir. This is J transport D, sir, only. So 33.
Yeah, that's what I'm saying.
Yes, sir.
33.14?
27.
Then
187548.97.
187548.9. Okay. This minus lambda into A. Huh?
Yes, sir.
Is the class following what I'm doing? Can somebody confirm? I can't see you. Can you say yes?
Yes, sir.
Okay, so you're following. Okay. Yeah. What is this, Suraj, now?
33.107.
This won't change.
Yes. 187548.97.
Yeah. Is it changing at all? So just it's a very small change. So it is really making a big change? Or?
No, sir.
Then why did we choose 0.001?
Actually, there a small change, but to get a correct result, sir.
You get correct result. See,
Yeah,
he's doing rigging. See, Suraj is doing rigging. Okay, so Z transpose T plus lambda I equals Z transpose T. Okay, so delta A.
1.764 and B 0.0053. 0053.
What is A new?
36.76 and B 0.0093.
Okay. Now please show the errors before and after. So please show the errors before and after. Okay. So now you can see that the first iteration, 0th iteration, the errors, sum of the square of the errors were 1054. Now, after the first iteration, it reduced to 117.24. But the Liebenberg-Marquardt algorithm seems to have worked more efficiently yesterday. Okay, but we had a lambda of 0.1. But now what happens is, you may ask, why did we not choose lambda equal to 0.1? Suraj, just go up and choose lambda equal to 0.1.
Okay.
Lambda equal to 0.1 causes violent changes in the answer. See, he's actually, he has automated it.
Yes, sir.
Come down. Lambda equal to 0.1. It causes some violent changes. See that from 1054, it is becoming 2503. So therefore, lambda equal to 0.1 seems to be a very high damping. So for this set of conditions, it doesn't work. Therefore, whatever worked for a Liebenberg-Marquardt is not working for this. So how do you find, where is the hope? I mean, the hope lies in basically you have to solve, you have to get yourself solved. You cannot just like that, you cannot solve. Please work in the heat transfer problem. You'll get an idea what will be the initial values A and B. You work a lot in Tikhonov, you'll get an idea and then you have to proceed. So different people can get different answers. Different people can get different initial guesses. That guy who takes a sensible value, he will get a better answer. This is the Bayesian approach. This is the data science approach with prior beliefs. So your idea of there is one question paper, there is one question, everybody should get the same answer. I mean, it doesn't happen in the world. Okay, people are different. Their approaches to problems will be different. Their solutions can be different. Okay, so now Suraj, make it point not one. Left side, show it. Even point not one is giving some. It is okay. So what are the values of A and B after the first iteration for point not one? See, A becomes 29 and B becomes point not one. So there could be a combination of A 29 and B point not one. Okay, which could still give you the same value, which will give you a lower error, but that is not, that is far away from the truth. But if you see the next iteration, it picks up. First 0th iteration is in orange color. The first iteration is in green color. And now the second iteration is in yellow color. So it hits the right answer almost. I don't know. Correct answer is point not 7, right, Suraj?
Yes, sir.
Yeah, again, so it is not working well. Now let's go to point not 1. Okay. Now show us the results. If you go to point not 1, see that. Go to the left side. Yeah. Now you're able to see that from 1054, first iteration was 117. That's what we got it now. Second iteration becomes 24.6. Now, Suraj, can you show your MATLAB code and let it go to the third iteration and let's see how it converges. So show the MATLAB code for Tikhonov.
Okay.
And then explain. So today's class, we will complete this problem. And then I will tell you some fundas on what is the philosophical idea, what is the philosophical underpinning or the funda behind the. Just explain the code. Please explain the code to them.
Yes, sir. Here xt is a temperature, time, and y is temperature, and here lambda I have taken 0.001, and things are same. And this one you already know, y fit function, and this is derivative of the fit function. P is forcing factor, and for techno-regularization, this one I have written algorithm. This is Z transport Z, and E by is a identity matrix, and this one is inverse, and finally dv is delta A and delta B, and total iteration I have taken 50. Now I run.
Now he's running the script. So it is running. Bottom you can see the script is running and it gave the answer. Now you will plot. Suraj, you can plot 3 things. So plot this is basically B
versus iteration.
Okay, so you can see that within 3rd or 4th iteration, you are getting the answer. So you may be worrying, you may be thinking what happened, it is bad compared to LMA. So you can basically just stabilizes. You can see that it stabilizes. Okay, go to A.
Okay.
Plot A.
Okay.
Please send the code to them today.
Okay.
Whoever wants can. You can see within 3 iterations it reaches the answer. 48 is the answer, is it? 48
yes, 48 point something, sir.
48 point something. Okay. Now please see that it immediately converges. Please plot the residual, Suraj.
Okay.
Akula said, please fill up the attendance. What is the error?
Yes, sir. I'm plotting.
We say some too many output arguments. So we are giving you the Liebenberg GNA and this thing. So based on this, students who are in 5th year dual degree data science or 4th year dual degree data science or interested in inverse, you can come up with the codes for other problems also. We can start solving, experimenting with data. If you don't have data, there are many curated data sets available in the field of atmospheric science, electrical engineering, mechanical engineering. So you have to just search. Okay, take some data set and start playing with this. Okay, and that should be fun. So you can see that the residuals have come down significantly. All right. Suraj?
Yes, sir.
Okay, very good. Now, can we show a case? Go to the GNA code.
Okay.
Now, let us start with a bad initial guess.
Okay.
What could be a bad initial guess? Let's say we start with 10 degrees centigrade for A. And B, no, you just point not 2, you start point not 2. Now just it's a plain GNA, right?
Yes, sir.
Okay. So you've got everything there, is it? GNA, MA, LMA, Tikhonov, is it?
Yes.
Okay, just run it. So we are starting with some bad initial guesses. So plot the residual for the GNA.
Okay.
Or plot A, whatever, A, B.
Yes.
See how, but eventually it settles down, is it?
No, sir. This is incorrect answer.
This is an incorrect answer. Now, see whether Liebenberg will work on this.
Okay.
What is the lambda, Suraj?
Lambda is 0.001.
0.001. Just try Liebenberg.
Okay.
See, ideally, this course should be run with everybody will come to the class. You should bring your laptop. You should solve problems like this. We should give a big, there should be a 6-hour exam and this should be a 12-credit course. But in that case, I want only 20 students in the class. If 100 students take, we cannot do this. Is this again incorrect answer?
Yes, sir.
Okay. Now, if Tikhonov also doesn't work, we are in trouble, man. Okay. Anyway, I told in yesterday's class that nonlinear regression is a strong function of initial guess. If Tikhonov also doesn't work, then where is the hope? Go to Tikhonov. So you can see that a simple A into 1 minus e to the power of minus bt can tease you.
Techno, sir.
Tikhonov. Okay, very good. Doesn't work.
Okay.
Correct?
Yes.
Just plot it. See, it is violently oscillating. Okay, but what is the way out then? Where is the hope? Okay, so first we proved that lambda can decide the fate. Number one, the initial case can decide the fate. Okay, now what it really means is, so if this is your A and this is your B, and this is your domain, okay, and let's say that this is the optimum solution. Optimum solution is S min. Okay, is reached. What you should do? So, if you are able to start from anywhere here, please note, if you are able to start from anywhere here, you are able to approach this either through Liebenberg or Tikhonov. But if you are somewhere here, Then Gauss-Newton, impossible. Liebenberg, there may be a chance. Tikhonov, there may be a chance. To come here is going to be very difficult. But this is actually the domain. This is actually called the parameter space. It is the playground with which you play the estimation of the inverse problem. Okay, so this playground is vast for a n-dimensional problem. Okay, or where n is high, it could be a high dimensional problem. But there are many parameters to be retrieved, so it will become a helter-skelter. You don't know where to start with. Therefore, there could be other algorithms. You can start with something like a heuristic method where you use genetic algorithm. You basically start with a non-calculus based technique and somehow get to this region. Then once you get to a region close, then you fire the calculus based technique. So this is called a hybrid approach to solving the inverse problem. So what we can do now is, so where is the hope for you? There is a hope. Never lose hope. Okay. What I will do is, because if you're a practicing engineer, if you're a practicing researcher, what we will do is, so I will take from A equal to, A is a temperature excess. I know it is some bucket, dipper, immersion heater, or it's some heat sink. I know that temperature will be 70 or 80 degrees. Therefore, theta has to be 70 minus 30, T minus T infinity is about 40 degrees centigrade. So what I will do is, I will take theta equal to 10, 20, 30, 40, 50, 60, 70, 80, divided into steps of 5. I will take 20 values of theta. Now I take some average in that. So I will take some average. Okay. Once I put the average, let's see the average is about 35 or 40. What is it? 40 theta. That means temperature is 65. Now theta equal to A into 1 minus e to the power of minus bt. Since I've taken the average as an assumed value of A, theta by A is known. 1 minus e to the power of minus bt, I will linearize. And then I will use simple least square regression. I'll get an approximate starting initial value for D. Okay, that will be the time constant. Then let's say that comes to about 0.005 or something. So I'll start from 0.001 to 0.01 or something, divided into 15 or 20 parts. So I'll have 20 values of A, 20 values of B. I have 400 pairs. For each of these 400 pairs, I run the forward model. Okay, for each of these 400 pairs, I run the forward model. And then find out in which region where I will choose S should not be greater than this. So I will find out the region where S is reasonably small. Then I can take some middle of that region. I can fire my Gauss-Newton algorithm or Liebenberg. This is one approach. The second approach could be, I take this 400 pairs. Watch data science guys, watch this very carefully. Other people don't worry. You can just close your ears. You have not listened to what I have taught, what I'm speaking now. It won't come in the exam. Okay. Data science guys, people who are interested in data, or general students of inverse who are keen in going to the next step forward, which is always bordering on research. Watch. What I will do is, I will take this 400 sets of A and B. Then I will develop a neural network, okay, which is a nonlinear regression tool. I will use one hidden layer, two hidden layers, whatever. And the output could be the temperatures, or the output could just be the residual. Okay, output could just be the residual, or it could be just the temperatures. Then what I will do is, I will now computationally work out for all those values of A and B, which are not in my original training set of 20 pairs of 20 values of A, 20 values of B. I will use a neural network to drive and get the residual. Then I can use an exhaustive search. I can use million points. Out of these million points, I will pick and choose that point which has got the minimum value of S. Okay, or I can work out in a probabilistic fashion the most likely estimate of A and B that subjects which will make the S minimum by taking a joint probability density function, which is actually the Bayesian approach, which I'm going to talk next week. So there are multiple ways of attacking the problem. If you keep your eyes and ears open, if you're not getting stuck in F equal to F of X plus A equal to F of X plus dou F, but that is only one way. There are multiple ways. There is a forward model. There is a set of measurements. I can do magic with it. So if you just shed that calculus and proceed forward, so plenty of opportunities are available to you. You come back to calculus, but only after you decide only after you reduce your feasible parameter space to a parameter space which is tractable, with which you can easily work out the solution based on a calculus based technique. So please, Suraj, you can just switch off your, I explained some advanced things. I hope some of you did. Even if one or two people have, if some of you caught what I said, you can just put a thumbs up. I can't repeat it because I spoke very fast. So, okay, so you got it. So people who already worked in neural networks would have been able to connect to what I'm saying. Otherwise, also you watch the recording, so you will get an idea of what I've said. What I'm basically saying is there are other ways of reducing this and then getting a, in simple English, I said there are better ways of getting a good initial guess to proceed with these techniques. So we stop with the Tikhonov today. Tomorrow we will spend one class on the Jacobian, which is so important. That is a Z. What are the scientific ways of getting Z? And then Monday we'll do the Bayesian. Okay. We'll stop here. Thank you very much. Tomorrow 9 o'clock.